Today I want to talk about motion along a circle, which actually later on will be important for all pieces of machinery which rotate, because so far we still are going to talk today about the particle. Now if you look at the piece of rotating machinery, a rotating piece of machinery, you can recognize that the particles constituting that object all move in a circle. If you, for example, sit in a car and you drive and you observe what the wheel is doing, all the particles of the wheel are moving in a circle. In a description of motion of a rotating object or along a circle for a particle, and we can consider even a planet as a particle if we look at the solar system as the object. There is a certain one more product which is useful. So how many different multiplications do we know so far? 3. Correct. Multiplying, we know how to multiply two numbers. We know how to multiply a number by a vector. We know how to use scalar product. Today, I want to start with a mathematical digression and introduce you to a fourth multiplication. In this multiplication, which is referred to as the vector product, also in common language, we often say cross product. And from now on, I will ask you that you use cross only for this type of multiplication, because in high schools, you use cross to multiply number 2 and 3. From now on, I don't want you to use cross for multiplying numbers. Reserve it for multiplying vectors in a vector product. Now, vector product is called not because it's a product of two vectors. Say it to yourself. It's not because it's a product of two vectors. Important thing is what is the result. And the result of vector product is a vector. Yeah, if you look at, because very often students make a mistake that scalar product is multiplication of two scalars, in other two numbers. It's not. Scalar product is also multiplication of two vectors. Why is it called scalar? Because the result is a number, correct. So in a vector product, the result is a vector. So here is a formal definition of vector product. Important thing is that the result is a vector. This is a notation of vector product. Very often people forget and think that this is vector product. Now, see what that product really represents. Magnitude of the vector product is equal to magnitude of the first vector times magnitude of the second vector times sine of the angle between these two vectors. Well, if we look at the vector, it always has magnitude and direction. So I took care of magnitude now. Now I have to specify the direction. The direction is perpendicular to the plane formed by these two vectors, which means that it is perpendicular to each of those two vectors. And, well, if I think about perpendicular to two vectors, I can, so let's say that I have one vector like that and one vector like that. Show me perpendicular direction to both, simultaneously to both. So up, for example, is perpendicular. Can you find another perpendicular? Down, correct. Well, so we have two options. Now, we cannot say that the result is up or down. We have to make sure which way. So from those two, we have to select one following the right-hand rule. And this is how we define this product. So Why do we have to use right-hand rule to determine the direction of vector product? Because this is how we decided. We decided that way. Now, I have to show you how to use right-hand rule. So let's say that I have two vectors, one in this direction, one in the other direction. And actually, I'll show you how I use right-hand rule. But this is not the only way. You may develop any other way so that you remember the directional relationship. Because in principle, one doesn't need to use right-hand rule if you develop a certain way of figuring out what will be the direction. But you have to develop such a method of making the conclusion that it never fails. All right. So let's say this is the angle between the two vectors, which is needed for calculating the magnitude of vector product. Now, for this product of vector A and B, the vector product is going to be indicated by the thumb. So vector product is up. Now, the way I do it, I align right hand. First I align the entire hand with the first factor, with the first vector. So here it will be vector A. Then I turn my hand until I can bend the remaining 4 fingers in the direction of the second vector. So if I have vector A is in this direction, I align my right hand with vector A. Now this is vector B. So I have to turn my hand so that I'm able to bend my fingers in the direction of this vector. Now the thumb says which of the 2 perpendicular vectors I have to choose. Do you understand that? All right. Do you understand how to multiply now these 2 vectors? Let's do an exercise. Multiply vector I and j. Talk to each other. What is the result? I heard already 0. What 0? 0 vector. Consider 0 vector. Maybe it is 0 vector. I want more discussions. And if somebody is willing to give his or her justification, I will give a microphone. Would you like to do it? Okay, I'll give you a microphone. Which way? Well, let's see. Which way did you figure it out? What will be the result of multiplying vector I and j? Not z. Z is not a vector, but you are right. What is the vector along z-axis? The base vector k. Correct. This answer is correct. Why don't you tell us how did you do it? All right. So how about if we think about the directions? Which way do you want what? So. So let's say that this is x direction, this is y direction, and this is z direction. Okay, so I is in this direction, j is in this direction, k is in this direction. All 3 are unit vectors. Okay, go ahead.
Okay, well, just start with I and put your hand out like that. Turn it to where you can rotate up and down, then point your fingers towards the j, and then the resulting is
right. Yeah, because vector I is in this direction, so first I have to assign my right hand. Now I have to turn it in such a way that I'm able to align the remaining 4 fingers with vector j. So thumb now indicates this direction. So it is a vector which is perpendicular to I and j, which means that it is along z-axis. It's either that way or that way. Right-hand rule says it is that way, which means that it is the direction is consistent with vector k. Well, are we already happy that that the result is vector k? No. Can you give a justification that it's vector k? Yeah, because right now we determined that the direction is indeed consistent with vector k. Maybe somebody else would like to say, oh, you know, you see the answer. Do you know the answer? No? Who knows the answer? Jessica, how about you? Do you know that? Well, what is missing? Why I'm not happy that the result is vector k? We have already determined that the direction is in the direction of vector k.
You don't have the magnitude.
We need the magnitude. Right. Think about the magnitude. Well, so magnitude of a result is magnitude of the first vector. What is magnitude of the first vector? 1. Magnitude of vector I was 1. What's the magnitude of vector j? 1. Correct. So we have 1 times 1. What's the angle between them? 90 degrees. Sine of 90 degrees is how much? 1. So I multiply here 1 by 1 by 1. The result is 1. Magnitude of the resultant vector is 1. Therefore, it is vector k. Let's multiply. Why don't we multiply now j and k? Multiply vector j and k. Yes? It will be vector I, correct? Yeah, because now this in the same coordinate system which we discussed just a moment ago. Vector j is up, vector k is that direction, right? So when I align it, now I am able to bend the fingers in the direction of vector k. This one indicates the direction of vector I. Why don't we multiply vector k and j? Oh, isn't it the same thing as just I asked you? Yeah. Oh, it is? Multiply it. Yes? It's different. If I multiply now vector k and j, I got a different result than when I multiply vector j and k. Do I say the same product or not? Do I mention the same product or not? What's the difference between the two products which I ask you now to calculate? Once I ask you to calculate product of vector j and k, and then I ask you to calculate product of k and j. Not directional, it's the order. Vector product depends on this, what is the first factor and what is the second factor. Let's take a look actually at more at various theorems which vector product does. Now let's say that if I multiply vector, I multiply vector 2i by vector j, what am I going to get? I'm going to get 2k. How about if I multiply vector I by 2j? Also 2k, right? So actually, if I multiply one of the vectors by a number, and it does not matter which vector I multiply by a number, I can associate that number with any vector, and actually I can take it even outside and recognize that no matter what I multiply, I can multiply one vector, the other vector, or the result. Vector product is kind of mixed associative law because it involves two multiplication. No, it's not one multiplication. We have multiplication of two vectors, vector product, and multiplication of a vector and a number. Let me give you a puzzle. Does vector product have the same property with scalar product? So for example, can I write down that, let's say, vector A multiplied by vector B multiplied by vector C, is it the same as multiplying vector A by vector C and multiplying it by vector B, and all of it together multiplying vector C by vector A and B? Are these true? Consult with each other. Anybody has an opinion? Do you have an opinion on that? Can you multiply it? Yeah, okay. What's the result? Let's figure it out. How are we going to get that vector? Why is it a vector? Why the result is a vector? Where do we have number? I think that everywhere we have vectors.
We multiply B times C in the very first.
Okay, let's see it. We multiply B and C, we will get a number. And then we are stuck. Yeah, multiply number 1 by vector I using vector product. What's the result? This is undefined operation over here. We need a vector in order to use vector product. Be careful about it. Because I bet that on the test, 1/3 of you will have no problem with that. You will perform operation. Most likely the result will be a number, by the way. All right, so this operation here is undefined. We cannot do it. We will have to change it to a different product. Which product? Number times a vector. So if we use an ambiguous notation, what symbol would we use? The bullet, correct. Well, the same thing is here. This doesn't make sense over here. This makes sense here. We can multiply that. Do you see that? Right? Because product of those two will give us a vector. And if we multiply it by, then we can multiply it by C. So how about, why don't you perform operation of multiplying I, J, and K? What's the result? As a hint, I'll tell you it's a number between 0 and 10. How do I know that it's a number, by the way? Because it's a scalar product, right? I multiply these two, this is a vector, and this is the last operation. The last operation is the scalar product, so it's a number. The result is a number between 0 and 10. 1, correct, right? Because if I multiply vector j and k, what vector I'm going to get? I. So here I have I square, scalar square, right? Or I can say that, let's go directly from the definition. It will be magnitude of the first vector, which is 1, magnitude of the second vector, which is 1, times what? How we calculate scalar product? Times cosine of the angle between these two. What is the angle between vector I and I? 0. Cosine of 0 is 1. All right. Now, we have already noticed that if we multiply the two vectors, it matters in which order. So if I multiply vector I and B and A, the two results are going to be opposite. Well, we can see that no matter that the magnitudes have to be the same, because it's magnitude of the first times magnitude of the second. This is magnitude of vector A times magnitude of vector B times sine between them, sine of the angle between them. Now, when we multiply magnitudes, we multiply numbers. So multiplication of numbers is commutative. However, I mean, if we use a right-hand rule, we can recognize that if I multiply, let's say that this is vector A, this is vector B. So if I multiply A times B, I have to align my hand with the first vector and then bend the fingers toward the second vector. So now I get thumb up. However, if I do it this way, in order to bend the fingers in the direction of vector A, I have to bend the hand like that. So I got a vector which is opposite. Vector product is distributive over addition. Which addition? If you look at this expression over here, it is distributive over what? Addition of vectors, correct. Now, is it, let me ask you now a question, is it distributive also over addition of numbers? What vectors do I have? A, B, okay. Is this true then? Who believes that it's true? Who believes that it's wrong? Okay, there are too many of those who don't believe anything. I want to have a conversation with your neighbor to figure out if multiplication, if vector product is distributive over addition of numbers.
Those are numbers. But yeah, that's definitely not.
Josh, what do you believe?
It's undefined.
It's undefined operation. Correct. You cannot perform this operation, although I know that 1/3 of you will perform this operation on the test. Now, why you cannot perform this operation? Let's start. What class do we have here? Addition of numbers. The result is going to be a number. Can we perform this operation? No, because vector product requires that both factors are vectors. So we cannot perform the operation over here. We cannot perform operation over here. We cannot perform this operation. Vector product, like every other product, follows the product rule when we differentiate it. So if both factors are functions of a certain variable psi, then when I calculate the derivative of a product of the vector product of those two functions, so these would be vector valued functions. I can, for example, multiply position of a particle by a force exerted on a particle. We will find out that this quantity, we have such a quantity. That quantity, by the way, is called torque. And we can calculate derivative, how it changes with time. I mean, we will have a lot. I mean, we will not actually calculate derivative of torque. We will be more interested in the derivative of angular momentum, which also requires is defined through a vector product. However, if you remember that when I brought up derivative of product of numbered valued function, I ask you not to switch the order. and the reason was vector product, because vector product is not commutative, so now it matters that the first function is always in front in order to have plus. Because for a numbered valued function, you could learn it that it's derivative of the first function multiplied by derivative of the second function plus first function multiplied by derivative of second function, or you can say that it's derivative of the first function multiplied by the second function plus derivative of the second function multiplied by the first function. Consult with your neighbor that you comprehend my statement. So what did I actually say? Because I know that I was spitting a lot of words in very fast and could be confusing. So what's the difference between the two things which I said? Andrew, have you comprehended it?
Yeah.
Okay. Can you repeat it?
Well, essentially order mapping. You have to do, you can't do, derivative function multiplied by the second.
Correct. You cannot have a term derivative of the second function multiplied by the derivative of the first function. Yes?
And is that because of the anti-commutative?
Correct. It's because of this property. Yeah. If we change this vector product here, we will get a term which is opposite. Now, I want actually because so far we were multiplying vectors I, J, and K. Now, how about if I know scalar components of a vector and of both vectors, and I will multiply. I want now to find out scalar components or components of the resultant vector. All right. So let's say I want to multiply vector A and B. Scalar components of the first vector are AX, AY, and Z. By the way, this term therefore would be called what? AX times I will be the vector component of vector A. And I expressed what I did over here. I expressed vector A in what terms? Well, you can say in terms of vectors I, J, and K, right? But I want you to use a nice scientific phrase. If I calculate such a sum of vectors I, J, and K, what is that sum called? A what? Well, yes, it is equal to vector A. I'm trying actually to find out to hear that it's a linear combination of base vectors. Say it. Correct. What are the base vectors? I, J, and K. All right. Well, I did the same thing to vector B. In other words, I represented vector B as the linear combination of base vectors. Correct. Now, I will use properties of vector product that I will use associative law. I will also use anti-commutative law. But first, I will use associative law. Well, associative and distributive law. No, I will use distributive law now and associative law. Now, if I use distributive law, I mean, if I have two sums, when I use distributive law, what is the effect of the distributive law? When I multiply two sums, that each term from the first sum is multiplied by each term in the second sum. So I could write down here I have AXI multiplied by BXJ, BXI. Now AXI multiplied by BYJ. Note that I use the associative law as well, because now, let's say, if I multiply the first two vectors, I pulled out the numbers in front and associated the two vectors together. Well, so you can actually check that. I mean, I don't think that I made a mistake. These are all 9 terms which you would obtain by multiplying each term from the first sum by each term of the second sum. Now, note over here that I have products of the base vectors. And I'll now take advantage, group those terms. I would recognize what is the result. Where if I multiply vector I and j, we already found out that it is vector k. Somewhere I have multiplication of vector j and I. So the result for that is minus k. Right? If I change the order, I will get a vector opposite vector. Yes. So these two. This one has k, this one has minus k. Let's start with this one. What's the result of multiplying vector I by vector I? How did we get that? No, I mean definitely not 1. Yeah, why is it called vector product? Because the result is a vector. What's the direction of vector 1? There's no such vector. We don't have vector 1. All right. So if I multiply vector I by vector I should get a vector. 0 vector, correct. How did you get that it's a 0 vector? Shout. Who said 0? Yeah. How did you get it?
Vector product of 2 vectors is 0.
Because what?
I don't know exactly.
Oh, so you guessed. Anybody knows why? Why it is 0? Because the angle between them is 0. So if you look at the magnitude of the result, it will be 1 times sine of 0 degrees. Sine of 0 degrees is 0. We will get a vector whose magnitude is 0. Only one vector has magnitude of 0. It's the 0 vector. Right? So even when you say that, for a while, later on, when you will be engineer, you won't even bother saying it. But right now you confuse zeros. So make sure that when vector I times vector I is not 0, it is a 0 vector. Right? Okay. How about JJ? And KK? 0 vector. Yes, so those three will result with 0 vector. Now, look that over here I have I times j and j times I. This one results in k. This one results with in minus k. Now here I have j times k. The result is I. Here I have k times j. The result is minus I. So these two, I can also combine these two. And now k times I, we didn't perform this operation, but it's equal to j. And you can recognize now that this one will be minus j. So I can group those together and express, I mean, when I order it neatly, I will get these components for vector product. So x component of vector product requires that we take y component of the first vector, multiply by z component of the second vector, and subtract third component of the first vector, multiply by the second component of the second vector, and so on. Actually, those of you who are familiar with matrices, and if you calculated determinants, you can actually kind of memorize this expression by writing determinant of such a matrix. In the first row, you need to put the base vectors in this particular order, I, j, and k. The second row of that matrix should be scalar components of the first vector, and the last should be scalar components of the second vector. So if you are familiar with determinants, you would know how to perform this operation, and you would really get that. If you are not familiar, you have two options. Well, memorize that. I don't want you every time to go through this calculation. Memorize this, or even better, learn how to calculate the determinant of a matrix 3 by 3. All right. How about if it, well, let's use now this matrix to find out a vector product of vectors I and j. So how would I write the determinant? What should I write in the first row? Look at the screen. I, j, and k. Now look at the screen and tell me what should be the second row. A what? Well, no, I mean, pick up appropriate ax, ay, and az for vector I. What is ax for vector I? In other words, you have now to represent. Look what ax, ay, and z are. These are the coefficients in what is that sum called? In the linear combination of the base vectors. All right. So if I want to represent now vector I as a linear combination of vectors I, j, and k, what numbers do I have to put here? 1, 0, 0. Correct. So scalar components of vector I are 1, 0, 0. Right? Therefore, I will have to put here 1, 0, 0. What should be the third row? 0, 1, 0. 0, 1, 0. All right. Those of you who know how to calculate determinant, you can think it in your mind. Now I will use the row above. The row above says that the first term next to I has product of 0 times 0. Yeah, this is ay times bz minus az times by. Right? Do you see that? I mean, I'm not looking at the screen. I'm looking at the determinant. I really calculate determinant. So if I multiply these, I will have 0 times 0 minus 0 times 1. So it's 0i. Plus, let's now go for vector j. If you look over there, it will be az multiplied by bx minus ax multiplied by bz. Well, so 0 times 0 minus 1 times 0. So it's 0j plus. And for k, I will have ax by minus ay bx. So it will be 1 times 1 minus 0 times 0. So it gives me 1k. So the result is k. Yes?
In my calc class, we were told that like the signs alternate. Like,
Well, yes, I was doing it that way too. Yeah.
Something like where it's like minus j plus k.
Correct. I mean, over here, look over here, we have it. So here we have plus sign, here we have minus sign. Over here we have plus sign, over here we have minus sign.
I know that, but I mean in between like each one in between I and j.
Ah.
In between j and k.
Okay. Then you have these terms different.
Yeah.
Yeah, the order of these terms different. Yeah, so whichever way you learn how to calculate determinant, use that way. So if you write down vector product in such a form, use whatever method you learn to calculate determinant. Because some people add columns over here. I don't, for example, I just look at those 9. I don't know what other, well, some of them just expanded. Whatever you use will be fine. But how about if I now multiply vector, let's say vector I by a vector along a diagonal. 1, 1, 1. The result, or maybe something that we know, we will know the answer. Yeah, okay. Let's not take the diagonal along the cube, but the diagonal of the base. Okay, so now I multiply vector I by a vector like this. All right. So let's do it mechanically. So next to vector I will have 0 times 0 minus 0 times 0. So it will be 0 I. Plus next to j, I will have 0 times 1 minus 0 times 1 minus 1 times 0. So it will be 0 here as well. Oops. Plus, now for k, I will have 0 times 1 minus 1 times 1. So it will be minus 1 times k, which means that the result is going to be minus k. Now let's see if from the definition we also will find it that way. So let's start with finding magnitude of vector product of vectors whose scalar components are like that. So the first vector is vector I. What's magnitude of vector I? 1. Correct. The second vector has scalar components 1, 1. So it's in this direction. What's the angle between these two?
45.
45 degrees. Correct. What's the magnitude of this vector? It's 1 in this direction and 1 in that direction. So it's diagonal of
Root 2 over 2.
square root of 2 over 2. All right. How about if, therefore, the magnitude of the product is going to be 1 times square root of 2 times, no, it's square root of 2, not square root of 2 over 2. It's longer than 1. Right? Now we have to multiply it by sine of 45 degrees. And that one is square root of 2 over 2. This one is square root of 2 over 2. So if I multiply all of these, I will get 1. All right, so magnitude is 1. Determine now the direction. And the first vector is in this direction. Second vector is in this direction. So it's down, right? Which means that it's minus k. Do you see it? All right. Let's now go to the next one. I want now to use it to analyze a motion which is called a uniform circular motion. And uniform circular motion is a motion with a constant speed along a circle. So for example, if I stretch my hand and keep this mouse over there and start turning at a constant rate, that mouse was moving in a uniform circular motion. We can even think about the angle with a particular direction and the instantaneous instantaneous position vector as an angular position of the mouse. So, for example, I can say that I choose this direction and consider the angle over here as the angular position. If it is uniform circular motion, it means that the rate at which the angle changes is constant. In general, that, well, that rate is just the derivative like any other rate. When we calculate a rate of change of a certain quantity, we take derivative. So if it is uniform, that derivative happens to be a constant. And let's say that this constant is called omega. Well, if it is omega, it means that this angle is proportional to time, with omega being the proportionality coefficient. So this angle here, if I write it down explicitly as a function of time, I should write down that this is omega times t. Well, if I introduce now a coordinate system, then I can write down, and I pick a convenient coordinate system. Have you noticed that? How convenient? What is the convenience of this system? Z is always 0, right? So I arrange xy plane in such a way that the motion takes place in that plane. Well, so if I write down scalar components of the position vector, the first component is going to be r times cosine of that angle theta. I project it over here. Y component will be r times sine of this angle. I project vector on the y-axis, and z is always going to be 0. Well, let's now take a look at velocity. We are, graphically, we mark it as an arrow, and remember that velocity is always going to be tangential to the trajectory. And since the object moves in a circle, trajectory is a circle, which means that velocity is going to be tangent to that circle. Now, how about if we find out scalar components of this velocity? Well, the simplest way is to do what? From the information which you have on the whiteboard, on the screen. The simplest way will be to take the derivative of position vector. All right, so I take the derivative of position vector. Derivative of, here we have a composite function. Derivative of cosine is sine of the same, minus sine of the same argument, and derivative of internal function is omega. So I take that omega over here. Derivative of sine function is cosine function, and internal derivative of internal function is again omega. So I use that omega twice for both terms. Derivative of a constant function, constant zero function is 0. So I got expression for this derivative. Now, you can, really you can recognize that if I make up a vector whose scalar components are 0, 0, omega, velocity vector results from multiplying this vector by position vector. Do it home. Yeah, so see what will happen if you multiply vector with these scalar components by vector with these scalar components. This way we avoid practically now differentiation. We don't have to differentiate. This vector over here is referred to as angular velocity of that particle moving in circular motion. I want to show you one more thing. Let's talk about acceleration. How do I find acceleration? Now, what would you recommend me to determine the acceleration?
The derivative of velocity.
Take the derivative of velocity. All right, so I'll take the derivative of this vector over here. So derivative of minus sine function is minus cosine function. I copied it over here. And derivative of internal function is omega, so I will have 2 omegas in front of that vector, and omega times omega is omega squared. Derivative of cosine function is minus sine, so that minus agrees with the derivative of cosine. And again, derivative of internal function is omega, so that omega squared takes care of it. And derivative of 0 is 0. Now you can recognize actually that r cosine omega t sine omega t and 0 is vector r. So really acceleration is minus square of this angular velocity multiplied by position vector. How should I mark then acceleration vector on the drawing?
Towards the center of the circle.
Toward the center of the circle, correct. Acceleration is toward the circle, toward the center of the circle. Well, now Newton's second law says that in order to have this acceleration, the net force must be in this direction as well. Oh, I can actually recognize that I can also relate magnitude. So magnitude will take, if I take magnitude of this one, of this vector, so it requires absolute value of the number which is in front, multiplied by magnitude of vector r. I can also recognize that if I take calculate speed over here, it will be magnitude of angular velocity times radius times sine of the angle between the two vectors, and angle is 90 degrees. So sine of 90 degrees is 0. So speed is equal to angular velocity multiplied by the radius of the circle. So I can write down that acceleration is also related to the speed, is proportional to the square of the speed and inversely proportional to the radius. So from that I can conclude that the magnitude of the net force which is exerted on an object moving in a circle must be well related to angular velocity and to speed. I want you to, by Monday, I want you to think about the moon. What is acceleration of the moon, and where that net force is coming from? And it will be on or to the next. See you